Hi everyone, welcome to our physics session for today. If you've joined for the earlier sessions that we had this morning, then welcome back. If this is your first session with us, then welcome to the My Tutor online school. This session is GCSE physics session, which is basically going to recap everything that was covered this week on the topic, which has been electricity. So if you're new to the physics sessions, then this session is led by our tutor Preshayla, who studies physics at Loughborough University. She's done lots and lots of lessons with my tutor, this being her fourth year as a tutor, but also she's been leading all of the webinars in physics so far. So hopefully if you're coming back, then you know Preshayla quite well. What you'll be covering today is, as I said, a recap of the electricity topic, so revising the topics that you've covered this week with Preshayla. Then you'll be doing some example questions, and then for the final 15 minutes, like always, we'll be taking the bulk of questions from you. If you do have questions as we go along, then feel free to drop them through into the chat box or through the Q&A, and either myself or Preshayla will pick those up for you. If you're new, then all of these sessions are recorded and you can find them if you join up to the My Tutor online school. So make sure you're signed up there. And just to say that this session will last for an hour. So I'm going to hand over to Preshayla now, who's going to lead the session.
Cool. So today we're just going to go through what we've been doing in this week, in the seminars this week. So I'll give a quick recap of the content covered, and then we'll go through some fast-paced questions. So we started the week off with current and potential difference. So it was all about this equation V equals IR, where V is potential difference and I is current and R is resistance. So here you can see we've got a simple circuit with a battery and a resistor. Now we know that the current through any component depends on both the resistance of the component and the potential difference across the component. Now the greater the resistance, the smaller the current, okay? So if we think about having a really small current, we're going to have a really high resistance. And you can think of it as the resistor kind of constricting that current, not letting as much current as it wants to through. Okay, so the resistor puts a constriction on the current. So if we have a very high resistance, we have a very small current because it's constricting it. Okay, so then we went on to talk about ohmic conductors. So ohmic conductors are just anything that follows Ohm's law. Now Ohm's law is V equals IR, and things that follow Ohm's law is just your standard fixed resistor or variable resistor. Okay, so just the standard one that you see, this box form here. Okay, so resistance is constant, it never changes in those fixed resistors, and therefore we have that potential difference is directly proportional to current. Okay, so potential difference is proportional to current because as one changes, the other changes in the same way related by resistance. Okay. So basically what that means is if potential difference goes up, current also goes up for a fixed resistance. So that was Ohm's law. Then we went on to talk about things that don't quite follow Ohm's law. So the first example that we looked at was the filament lamp. Now the filament lamp is a special kind of component that we find in electric circuits. So it's described by this rule here. The resistance of the lamp increases as the temperature of the filament increases. So what that means is in the lamp, we have a little filament, and as we push more current, more potential difference through the filament, it gets hotter and hotter. And it gets hotter the more you leave it on, the more current you put through. So if the temperature of the filament increases, then the resistance also increases. Okay, so it's slightly different to a fixed resistor in the sense that it now depends on temperature. Okay, so it's not all just about V equals IR. Here we have temperature coming into the equation. Okay, now this is the graph for a filament lamp, and it's this kind of snake shape, S shape. And this graph needs to be remembered, okay? So you need to be able to recreate this graph in an exam and know that the filament lamp produces a graph of this shape. Okay, so now we have our second example of a non-ohmic conductor, which is a diode. So you might remember that the diode circuit symbol looks at it as something like this. So that's our diode, and the arrow represents the current, which only flows in one direction. So the diode only allows the current to flow through in one direction, okay? So the diode, therefore, has a very high resistance in the reverse direction, okay? So if it has a very, very high resistance in the reverse direction, it's going to let not a lot of current through, okay? By Ohm's law, if we have a very high resistance, it doesn't let a lot of current through. And this happens in the reverse direction. In the forward direction, however, it only lets current through. In the reverse direction, it doesn't. Okay, and then we went on to talk about direct and alternating potential difference. So this was the second day, direct and alternating potential difference. So DC and AC, you might hear it called. However, DC can be misleading and AC can be misleading because they actually stand for direct current and alternating current. However, in this in direct and alternating current, we can replace current with potential difference. So direct and alternating potential difference is the same as direct current and alternating current. So we have two different forms of potential difference. It doesn't matter whether you say potential difference or voltage, they are the same thing. However, the exam board prefers and will use in their questions potential difference. So where possible, try to use potential difference, but do know that it does mean the same thing as voltage. Okay, now we talked about where we might find DC. Well, DC is found in car batteries, solar cells, cells that we find in our circuit, batteries that we put in our circuits, power packs, the batteries that you use at school, the batteries in a remote control, they all use DC. Okay, so direct current that only flows in one direction. So direct current only flows in one direction. That was the definition of it. Then the other type of potential difference that we have is alternating potential difference. So we don't tend to do calculations with this one at GCSE. We just need to know what it's all about. So for alternating potential difference, we have it coming out of our socket. So it's in our house, it powers our household appliances, it powers your chargers, your laptop chargers, that's all AC. Anything that you can plug into a socket is AC. Now it's also known as mains electricity. So mains electricity flows all throughout your house and into your sockets. Now the reason that it's alternating current is because it's made in power stations. And power stations use magnets to create the electricity. Because they use magnets, we get an alternating current rather than a direct current. So that's where the alternating comes from. Now, facts that you need to know about alternating current and about mains electricity is, first of all, that it's generated at a frequency of 50. and it's delivered to houses at a potential difference of 230 volts. So they are simple recall facts that you must know, you must memorize, and they may ask you, what is the potential difference of mains electricity? That would be 230 volts. And what is the frequency of AC mains electricity? Well, that would be 50 hertz. Okay. Then we went on to talk about how plugs are wired. So we had a lot of questions, a lot of kind of example past paper questions about earth, neutral, and live wires. Okay, so earth, neutral, and live wires. There are 3 different copper wires in our plug, and they're coated in this coloured plastic. Now, the colour of the plastic lets us know which one we're talking about. So here you can see that the earth wire, you might remember, is green and yellow stripes, the neutral wire is blue, and the live wire is brown. Where we have a fuse and a cable grip and the outer insulation of the wire. So all very important features of the plug, and we need to know what they do. So for those of you that were there in the webinar, hopefully you'll be able to answer this question. What is the earth wire used for? So what is the earth wire used for? Go and put your answers on the chat, or just think about it in your head. What is the earth wire used for? Great, I can see loads of you putting the correct answers on, which is, if there is a kind of surge in current, then it provides a path for the current to go to the ground so that we don't get shocked. So it takes the current and it pushes it into the ground so that it doesn't affect us, okay? Now that path, that earth wire, has a very low resistance. So we say that it's a low resistance path. The reason that it has a low resistance is to allow as much current as it can to pass through. So it wants to take all that current away really quickly and really effectively and efficiently so that we don't get shocked. Therefore, it's a low resistance path. Okay, so that's the function of the earth wire, which you got really good. Now, what is the function of the fuse? The fuse. So put your answers in the chat, or have a think about it. What is the function of the fuse? Great, I can see loads of you putting the right answers again. If the current is too high, then that will melt the fuse and it will break the circuit. Okay, so that the plug doesn't work anymore and it can't deliver a high current because the fuse has melted and it's broken the circuit. If you remember, the fuse has a rating. So a fuse might have 5 amps rating. That means that any current that is higher than 5 amps is not allowed through. Okay, so if the current is higher than 5 amps, it's not allowed through. And we talked about picking an appropriate fuse rating so that the current that is going to come through is allowed to come through, but not big enough so that it doesn't detect a surge in current. So let's say you had a current of 3 amps coming through from a kettle or something. If the fuse detects a current that is higher than 5 amps, it will shut down, but the fuse is 5 amps, so it's going to allow our 3 amp current to come through. So it's about picking a sensible fuse rating for the current that we have. Okay, so if you weren't here for the webinar, here are the functions of each feature of the plug. So the outer insulation is just there as kind of a safety feature to keep all the wires together and give that extra sense of insulation. The cable grip is again just there to hold all the wires tightly. The live wire is what is actually allowing the current to enter the device, remembering that it's AC because we're talking about mains electricity, and that is held at 230 volts. So that's where the current is coming from, okay, and that's the brown wire. Then we have the fuse, which we just said melts if the current gets too high. We have the neutral wire, which is literally just there to complete the circuit and pull everything together. Then we have the earth wire, which is that low resistance path that takes the current to the ground should there be a fault. So that's, and again, another safety feature. It's really important for people to understand the safety features of mains electricity and plugs and sockets, because we obviously want to reduce our risk of electric shock. Okay, so that's one of the main dangers that we have. Okay, and then moving on, we talked about power. So this is when we did the electrical energy transfer webinar, and we were talking all about power and energy. So we started off with power, and we talked about these two equations for power. So we have our first one, which is power equals current times potential difference, and our second one, which is power equals current squared times R. So we had a few questions about what this little 2 means. It means that you need to square the current before you times it by R. So it's not 2R, it's not 2I, it's I squared R. Okay, so you can use either one depending on what information you're given in the question. If you're just given current and potential difference, then ideally we want to be using this one. And if you're given resistance, then it's always best to use this one. Okay. Then we went on to talk about the two equations for energy. So we just talked about the two equations for power. Now we're talking about the two equations for energy. Now this is energy related to electrical work, so electrical energy. So this doesn't apply for kinetic energy, gravitational potential energy, none of those. This is only for electrical energy, okay? So electric work energy. Now we have E equals PT, where energy is measured in joules, power is measured in watts, and time is always measured in seconds. We never measure time in anything else. Time is in seconds, so power times time for energy. And we use this equation for when we're talking about household appliances usually, and you'll see that in just a second when we go through power ratings, but this equation tends to be used for kettles, toasters, microwaves. They're the kind of common appliances that we can apply this equation to. So that's the first of two equations. The second equation that we have for energy, electrical energy, is Q times V. So charge flow is Q and V is potential difference. So QV, charge flow times potential difference. So this is the second equation for electrical energy, and this one tends to be used in circuits. Okay, so for the first of the two equations, E equals PT, we talk about it in terms of power ratings. So a power rating means that the appliance transfers whatever the power rating is, that amount of joules of energy per second. So say we were to have a 12,000 watt power rating, that's going to mean that the appliance that has that power rating transfers 12,000 joules of energy per second. Okay, so transfers, for example, if it was an oven, that would transfer 12,000 joules of electrical energy per second. into thermal energy. Okay, now you can see the various power ratings here of a few different appliances. So a clock would only have a power rating of 10. It only needs 10 joules per second to transfer it into mechanical energy. So the ticking of the clock, the electrical energy gets transferred into mechanical energy, but that's only needing 10 joules per second. It then goes up. As expected, a kettle would take more energy than a clock, and an oven would take more energy than a kettle. It's important to note that these are not the only power ratings, so not all clocks will have 10, not all kettles will be 2,400. These are just some examples of power ratings that they could be. So average power ratings for that appliance. Okay. And then we went on to talk about kilowatts. So power in kilowatts and power in watts. This is how we convert between the two. So we just divide by 1,000. And it's important to know how to transform watts into kilowatts, because sometimes in exam questions, they use kilowatts instead of watts. So we need to know how to transfer between the two. Okay, now we have the second of our two equations, which is E equals QV. So when a charge moves through a potential difference, energy is transferred. So it's really talking all about circuits, because we have a charge moving around the circuit, an electron moving through the wires in the circuit, which is being pushed by a potential difference. So that is where our energy comes from. Okay, so an electron flows through the circuit from being pushed by a potential difference. So we use this one for circuits. Okay, and then we went on to talk about the national grid. So power is transferred to homes from power stations using the national grids. So it's a system of cables and transformers that kind of combine together to make power be able to go to our homes. So they make up the national grid. And then we talked about the two types of transformers that we can have. So step-up transformers are used to increase the potential difference, and step-down transformers are used to decrease the potential difference. Okay, so step-up increases, step-down decreases potential difference. We use step-up transformers when we're going from the power station to the transmission cable. So this bit can get a bit tricky. When we are going from the power station to the transmission cables, we want a really high voltage in the transmission cables. Okay, really high voltage in the transmission cables. So we use a step-up transformer to amplify the voltage. So that's where the step-up transformer is used. Then it's in the cables, the voltage is flowing through the cables, but then the voltage from the cables needs to get into our homes. That's where the step-down transformer comes into play. So we have a very high voltage in our cables. We put a step-down transformer there to decrease the voltage into a much lower value, which makes it appropriate for domestic use. So that's when the step-down transformer is going to transform the potential difference to 230 volts. Okay. And then the final webinar that we had was about static electricity. So static electricity between two insulating materials, otherwise known as charging by friction. So when certain insulating materials are rubbed against each other, they become electrically charged. We have this idea of the transfer of electrons. So transfer of electrons is really what is fundamental to static electricity. The material that gains electrons becomes negatively charged, and the material that loses electrons becomes equally positively charged. Okay, so we saw that in our rubbing of the rod with the cloth in that diagram. Okay, and then we talked about two electrically charged objects near each other, and this was very similar to our magnetic fields and our magnets with the north and south poles. So if they are different charges, different poles, they attract. If they're the same charges, same poles, they repel. Okay, so as you can see in the diagrams here, we've got like charges repulse, different charges attract. We also talked about the electrostatic force, so the force that acts between electrically charged objects is called the electrostatic force. And this is a non-contact force, so you don't need to be touching it to feel it. And then we talked about electric field. So if we were to have a single charged object on its own, that's going to create an electric field around itself. So a charged object creates an electric field around itself. The electric field is strongest close to the object and weakest when it's far away from the object. We show this using electric field lines. So we use these radial field lines which point from positive to negative. So here we've got a positive charge, so they're going away from the positive charge because they go from positive to negative, and they come to negative. So in this one, they're coming towards the charge. So two things about electric field lines is that if they're close together, the field is stronger and the direction they point is always from positive to negative. Okay, so that was all the content covered quite quickly. If I have gone over anything too fast, the whole webinar is on YouTube, so you can have a look and follow it in your own time. But that was just a quick refresher of the webinars that we've done this week, and a quick revision of all the electricity that you need to know for your GCSE. So now we're going to do some past paper questions, and we're going to start off with our quick fire questions like we always do. So if you could please put your answers in the chat for questions 1 and questions 2. What is a flow of charged particles called, and what unit is charge measured in? Okay, great. I can see loads of you putting the right answers in. Current is the flow of charged particles, and coulomb is what we measure charge in. Okay, now questions 3 and 4. What current flows if 10 coulombs flow past a point in 2 minutes? So you need an equation for this one. And then for question 4, it's just what is potential difference also called? Okay, so if you're struggling a little bit to remember the equation is just Q, which is charge flow, equals IT. So charge equals current times time. Loads of you putting the right answer in the chat, which is A, 0.083 amps. The way that we got that is by doing the charge 10 divided by minutes, 2 minutes, remembering to change our minutes into seconds. So 2 minutes in seconds is 120 seconds. So we have 10 divided by 120 is 0.083. So well done if you got A. And then yes, potential difference is also called voltage. Okay, and then moving on to our next quickfire question. So can we answer 5 and 6 first? So 5 is if 25 coulombs of charge shifts 50 joules of energy between 2 points, what is the voltage between those points? And what current flows in a 100 ohm resistor if 5 volts is connected across it? So this really relies on you remembering the equations that we've talked about before. If you don't remember, the equation is E equals QV. So you're going to want to use E equals QV for this one. And we have V and R in the next one, so we're going to use our trusty V equals IR for the next one. Okay, so using our E equals QV equation for question 5, we can see that we have 50 divided by 25, where 50 is the energy, 25 is the charge. So if we do 50 divided by 25, we get the volts, which should be 2. So if you got 2, well done, that's correct. And then for the second one, what current flows in a 100 ohm resistor if 5 volts is connected to it? Well, that's going to be 5 divided by 100, so 0.05 amps. Okay, so 5 is the volts divided by 100, which is resistance R, equals I. And 5 divided by 100 is 0.05 amps. Okay, now for question 7, what type of conductor is a fixed resistor? So our normal resistor that follows normal rules, what type of conductor would it be? Great, loads of you putting ohmic conductors, that's absolutely correct. It's a normal fixed resistor that we find in normal circuits. So it follows our normal rule, which is Ohm's law. And then a 2 ohm and a 3 ohm resistor in series give what total resistance? So this is thinking back to our very first webinar. What do we do with resistors in series? Well, we add them. So if we have a 2 ohm and a 3 ohm resistor in series, we add them up to get 5 ohms. So the correct answer is 5 ohms. Okay, so 2 more quick fires. What power is transmitted by 2 amps flowing across 5 volts? And what power is transmitted by a current of 2 amps flowing through a 6 ohm resistor? So again, relies on you knowing the equations. If you don't quite remember them, P equals IV and P equals I squared R. Great, I can see loads of you putting 10 for the first one. You just times the current by the voltage, so we get 10. And then the power for the second one, well, you need to do I squared R. So we have I equals 2. I squared is 4 times 6 is 24. So 10 and 24. Well done. Loads of you are getting the right answers, which is really, really good. Okay, so a few definition sort of questions. Again, recall. What is meant by direct current? Direct current. Cool, I can see loads of you putting the correct answer, which is C. So current, that is always in the same direction. That is the definition of direct current. Some of you put B, and that's definitely an easy mistake to make because direct current just sounds like it should directly go to the component, but AC does that too. Current that travels directly to the component is kind of normal. It's not the defining point of direct current. Direct current is a current that always travels in the same direction. Okay, and then what about the next one? Electric power is transferred from power stations to the national grid. What is national grid? Well, the national grid is a system of cables and transformers linking power stations to consumers. So that is what the definition of the national grid is, us being the consumers of the electricity. Okay. This one you may or may not know, depending on whether you were there in the webinar, but the fuse is connected to which wire? So remember, the fuse is the thing that detects the current. So which wire does it need to be connected to be able to detect the current? Okay, it's really easy to get confused with this one, but the fuse is connected to the live wire. Okay, the fuse is connected to the live wire because the live wire is the wire which the current goes through. So to be able to detect the current, the fuse must be connected to the wire that holds the current. So the fuse is connected to the live wire. If there was going to be a surge in current, then it would be in the live wire. So the fuse must be connected to the live wire. Okay, so here they get a little bit more complicated. What happens to the resistance of a filament lamp as the current through it increases? So remember, this is kind of S shape here. What happens to the current as the resistance increases? Brilliant, loads of you put in the right answer in. It also increases. So the resistance increases if the current increases. Okay, because if the current increases, the filament gets hotter. If the filament gets hotter, the resistance increases. What is the difference between voltage supplied by a cell, so that would be direct current, and the voltage of the domestic main supply? So there's more than one, there's two differences between them. Have a go, put your answers in the chat, or just think about them in your head. What are the differences between them? Okay, you can see loads of you putting one of the correct answers. So yes, one is DC, which is the voltage supplied by a cell, and one is AC, which is the main supply. And some of you are getting the second one, which is really great because it's not obvious straight away. The cell has a much, much lower voltage than main supply. So main supply is 230 volts, but a cell is going to be somewhere around 1.5 volts. Okay, so one has much, much lower voltage than the other. Okay, so here we have a current potential difference graph. Which one out of A, B, and C, these are three different wires, has the greatest resistance? So this is all done using V equals IR. Which one would have the greatest resistance? So maybe this is kind of a hint that I would give you. For one potential difference, have a look at the current. So let's say at 10 volts, when each wire is at 10 volts, which current is the highest? Great, loads of you are putting C, which is absolutely correct. For the same potential difference, it's a much, much lower current. If it's a much lower current, it's a much higher resistance, okay? Because they're inversely proportional to each other. Current and resistance are inversely proportional to each other, which means if one goes down, the other goes up. So if we have a very low current, we get a very high resistance for a fixed voltage. Okay, that fixed voltage in our case was 10 volts. Great, let's move on. So this one we have V equals IR. Again, they've just put in it there for you in words. What would be the potential difference across the battery? So here we have two resistors, so don't forget to do the appropriate thing with those resistors. So remember, when we have resistors in series, we need to do something first before we can put it into in our equation. Cool, so you want to add the resistances to get 30 ohms. Then you can put 30 ohms and 0.4 amps into your equation to get 0.4 times 30 would be 12. So if you put 12 volts, well done, that's the correct answer. Okay, so for the next one, we have a power of 10,690 watts and it's connected to a 230 volt supply. What would be the current? So our equation is P equals IV, or rearranged, I equals P divided by V. So what would the current be? Given the power is 10,690 and the voltage is 230. So current equals power divided by voltage. Remembering to read the whole question, which says give your answer to two significant figures. So that would be one of the marks of the 4 marks. So it's really important when they do specify that you do it to two significant figures. So we get current is power divided by voltage. So current, which we're trying to find, equals power, which is 10,690, divided by voltage, which is 230. When you put that into your calculator, you get 46.48. And when you put it into two significant figures, you just get 46 amps. Okay, so the answer will be 46 amps. Well done if you got that. Okay, so this one includes quite a few steps and is a little bit more tricky. So it's going to be the last one that we do before I take questions. So it involves you using two different equations, the first of which relates charge to time. So it's that Q equals IT. So that's the first equation you need to use. That should give you I, which you can then use in this equation. So try to have a go at using those two equations to get you the resistance. So first of all, we need to find current. So current from this equation, when you rearrange it, you get I equals Q divided by T. We've been given Q is 18,000. And we've been given time is 300. So if we do 18,000 divided by 300, we get 60. So we know that our current is 60 amps. Now we can use that in the next equation. So power, we know is 13.8 kilowatts. Now, how do we get kilowatts into watts? What do we need to times by? Well, we need to times by 1,000. So 13.8 times 1,000 is 13,800 watts. So that's our first step, to convert kilowatts to watts. Then we can put it into our equation. So 13,800 equals I squared R. We know that I is 60. So I squared is 60 squared, and 60 squared is 3,600, which we times by R. Now we can divide both sides by 3,600 to get R, which you should get as 3.83. So really well done if you got 3.83. It's definitely not an easy question because it involves quite a lot of steps, but well done if you got there. Don't worry if you didn't. Maybe try to have another go after the lesson by yourselves using these two equations. Okay, so that's a few past paper questions done with you. If you do have any questions, please put them on the chat. I'll answer them now, and then if we don't have any other questions, then we'll go through a few more past paper questions.
Hi Preshayla, I've got some questions through. First question is, other than connecting the circuit, what other function does the neutral wire have?
So the neutral wire it doesn't have another function except for just being a connection in the circuit. If you probably have seen a plug has got 3 pins, so a 3-pin plug, it connects into one of the pins. So the neutral wire, its only function really is to be a circuit connector.
Cool. And then we had a question asking if you could please go over the earth wire in a circuit.
Earth wire in a circuit, yeah. So that will be... Okay, I can't find the slide right now, but the earth wire in a circuit is there as a safety feature. So we have 3 different wires. The earth wire is a safety feature. What the earth wire is there to do is, if there happens to be a fault with the plug or a surge in current, to prevent us getting an electric shock, it takes the current, the surge in current, and pushes it into the ground. What I mean by ground is it could be an electrical wiring underneath, underground, or a water pipe underground, or something like that, and it takes the current and it discharges it away, okay, so that it doesn't harm us and doesn't give us an electric shock. It's a low resistance path. It's low resistance so that it can allow as much current as possible to come through it.
Cool. Someone has asked if you can go back to the diode and filament bulb diagrams, and also someone wants to know what a circuit breaker is.
Okay. So this is the filament lamp graph, and it's described by if the resistance increases, the temperature of the filament increases, and vice versa. So it looks like this S shape when we have I on the y-axis and V on the x-axis, so it's that S shape. For a diode, it looks like this. So diodes mean that current is only allowed through in one direction. And then a circuit breaker is similar to a fuse. So you might hear it called a residual circuit current breaker, so an RCCB. And it's basically similar to a fuse, and it melts the wire and allows the current to discharge slowly.
Great, thank you. We also have some other questions that aren't necessarily about the topic, but about the upcoming sessions for next week. So the timetable for all the webinars for all the different subjects next week goes out every Sunday. So you can look out for what's coming up next week as well. A question for you, Preshayla, I think is, what grade are these questions?
So these will all be, they'll all definitely be in a foundation paper and in a higher paper as well. So the last question that we did would be definitely in a higher paper. The rest would all come up in both.
Cool. And if we take one last question and then maybe go through another question, a paper question. This last question is, which is better, a fuse or a circuit breaker?
It really depends on what appliance you have. So residual current breakers are the kind of safest version, and they still prevent electric shock, but they do it much quicker and much more efficiently. So it automatically breaks the circuit as soon as it detects a surge in current. But the fuse takes the wire in the fuse has to melt, and then if that does happen, you need to replace the fuse. So a residual circuit current breaker doesn't necessarily needs to be replaced. It's testable and resettable, whereas with a fuse you have to replace the fuse if it has melted. So I would say that residual circuit current breaker is much more effective and cost efficient and resettable. So definitely an RCCB is much better than a fuse. Okay, so we'll go through what I think is probably a harder question. If I can just find it. Okay, so with these questions, they are actually taken from the 2018 past paper. So the actual GCSE that was set in 2018. So they're really recent and really relevant to your exam board. So here we have a kind of diagram of the national grid, and it talks about transformers playing an important role in the distribution of electricity. So what is the role of transformers in the national grid? So it's a 4-mark question, so you need a lot of detail here. If you've got any ideas on what you might want to include in your answer, put them on the chat, and then I'll have a look and see if we're kind of along the right lines, and then tell you exactly where you might get the marks. So what is the role of transformers in the national grid? Okay, so transformers are really there to amplify the voltage and decrease the voltage. So if you remember, a step-up transformer increases voltage and a step-down transformer decreases voltage. So what the step-up transformer does is take the energy, the electricity, from the power station and amplify it to a much higher voltage. When it's at a much higher voltage, it goes through the cables. We want it at a really high voltage so that it can have as low current as possible. So remember, a high voltage means a low current for transformers. So it's at a high voltage in the cables because it's been amplified by this step-up transformer. Then when it gets to the other side, we have a step-down transformer. What the step-down transformer does is take that really high voltage from the cables, step it down to make it appropriate for domestic use. So that's when it's going to go from a very high voltage to 230 volts, which is then acceptable for domestic use. So they're really important, both step-up and step-down transformers. So it's important to know the role of them. Okay, and then we'll just go through one more question then. I think some of you are still a bit confused about what each of the wires in the 3-pin plug do. So for each of the functions of the wires, so for this question, why is it important to have a 3-core cable? The live wire is what is allowing that AC current to be delivered. The neutral wire is there as a connection, and the earth wire is there as a safety feature in case we get a fault, and it can discharge the current really quickly to the ground so that it doesn't harm us. The plastic casing on a hairdryer or some appliances just have a plastic casing can be a feature that replaces an earth wire. So a hairdryer may have a plastic casing. If the hairdryer has a plastic casing, there's no need for the earth wire. The reason for this is because the plastic casing is a really good insulator. So there's no need for the earth wire because the plastic acts as an insulator for the electricity. Okay, so that's all the questions that we have time for. This will obviously go onto YouTube so that you can access it if you do want to go over anything that we've covered, and also each of the webinars from this week will go onto YouTube so you can go into the content in more detail.
Great. Thanks, Preshayla, and thanks everyone for tuning in again. I really hope you enjoyed all of the sessions that we ran for you this week. And as I said, there'll be a full schedule for next week as well. This week we had our first chemistry sessions, our first biology and our first English. So look out for lots more to come next week on those subjects, as well as more physics and more maths. Have a lovely weekend, guys, and see you all next week. Bye.
Thank you. Bye.